This is chapter 6.1, exercises 29 through 38. I'm going to go over the odd number problems here, 29, 31, 33, 35, and 37. And this section of the book, 6.1, has to do with vectors. So we're going to be doing these vector exercises. In this first set, exercise 29 through 32, find the component form of vector phi. And here we're given a magnitude and direction form. So we're going to go to component form. And component form, if you can recall, is like you have like a coordinate pair but with angular brackets, and you'll have x and y. So you're looking for the x value of this point here at the tip or head of this vector, and what are the coordinates there. One thing I've been telling my classes for a while now is, in fact, sing a little song. Our cosine is x, and our sine is y. Okay? And so this 18 is like the r, or the radius, if you want to consider it that way. So what we're going to have is our vector and component form, the x-coordinate. So the x-coordinate is going to be, this is going to be our adjacent side of the triangle, and our opposite side is over here to the right. And what we have is r, which is 18, times the cosine, or x, the horizontal direction, of 25 degrees. And our y-coordinate is, this vector is 18 times the sine of 25 degrees. And really, this vector here is really our answer for that. Now, in the book, they're looking for a numerical answer, and so that's going to be roughly equivalent to what I'm going to calculate now using a TI Inspire CX calculator. And so we have, now make sure our calculator is in degrees. We see it as the upper right corner. So we have our magnitude 18 times the cosine of 25 degrees, and for that we get 16.31, we'll call it. Okay, 16.31 to 2 decimal places. And now for the vertical component, 18 times the sine of 25 degrees. So we get 7.61, we'll call it, round in the hundredth place. So we get 7.61. So either of these versions would be acceptable to me. And really, that's all there is to it. If we can just remember, our cosine is x and our sine is y, and r being the radius, if you want to call it that. And 30, very similar to 29. 31. Okay, we have this time our standard position angle is not within quadrant 1, but rather in quadrant 2. But the formula is still the same. And that formula is that we take our radius, if you will, 47, and multiply that by the cosine of our angle of standard position, which is 108 degrees. And then for our y value here, the vector. It's 47 sine of 108 degrees. And we got to be careful, because instead of 108 degrees, let's say coming from the other side, we had maybe 72 degrees, and we would get a positive value for the cosine if we use this same formula. We'd have to turn that negative. And this brings up the subject that when we find our 47 cosine 108 degrees, that number better be what? Better be negative, or else we've made some mistake. So we put in 47 times cosine 108 degrees, and we get negative 14.52 to the 100th place. Okay, and now for the other value, and it makes sense to be negative, right? Because over here to the left of the y-axis. And next we have 47 times sine of 108 degrees. We get 44.69, actually would round to 70, right? 44.70. So really, that's quite a simple problem. We're able to do this because we have this angle and standard position. Standard position and reference angle are the same in quadrant 1, but outside of quadrant 1, quadrants 2, 3, and 4, you got to pay attention. Are we given a reference angle, where we'll have to adjust the plus or minus for cosine or sine perhaps, or are we given a standard position angle for which we need to make no further adjustment? Next odd number problem is going to another set, and the exercise is 33 to 38. Find the magnitude and direction angle of the vector. So in 29 through 33 we had 32 we had a direction and a magnitude already. Here we're going to find magnitude and direction. And what this looks like is this. We have I'm just sketching XY coordinate plane. And we have the vector 3, 1, 2, 3 to the right, and 4 up, 2, 3, 4. And so we have this point over here at 3, 4, and our vector is an arrow in this shape. And this vector has a triangle, or we can use it to make a triangle by dropping a reference angle. And if we have this angle right here, then I'm going to label theta. This to the right is the opposite of theta, and to the bottom of the triangle is the adjacent side. Well, to find the magnitude, that's really a version of the Pythagorean theorem. So our magnitude, MAG, I'll just put an equal sign, is equal to, we're going to take the x-coordinate in parentheses squared plus the y-coordinate in parentheses squared, and take the square root of that. So we take this x-coordinate here, this 3, and plunk it right here, and this y-coordinate 4, plunk it right in here. And so when we work this out, we get 3 squared, which is 9, and we get 4 squared, which is 16. So 9 plus 16 is 25, so we have the square root of 25, which equals 5. So that's our magnitude. And if we were thinking much, we could have figured out that this is a 3, 4, 5 right triangle, because our opposite side is 4, our adjacent side is 3, so our hypotenuse will have to be 5. Now for direction, the sides we have are opposite and adjacent, the initial sides, so we know that the tangent of, we'll call theta, equals our opposite over adjacent, which is going to be 4 over 3. And we want to find the direction, so we need to isolate that direction, and to do that we can take the inverse tangent, put tan -1 of this quantity inside. And what that does for us is, on the left side, the inverse tangent of tangent theta is going to be simply theta. And on the right side, we have the inverse tangent of 4/3. And for that, we can go to our calculator. So we go to trig, go to the right to tangent, and down to inverse tangent, and that's going to be of the fraction 4 over 3, and for that we get 53.13 degrees. So here we go, 53.13 degrees. Now we're fortunate in one respect here, and that is that since we have our angle in quadrant 1, there's no adjustment we have to be making as far as for quadrants 2, 3, and 4. So anyway, that's it. Problem 34 is not quite as straightforward, in that with this angle at -1, 2, you're not in quadrant 1. Let's go on to 35. Now 35 is written as in terms of standard unit vectors I and j. Okay, so, and those standard unit vectors are, I is equal to the vector 1, 0, and j is defined as the vector 0, 1. So we can go ahead, and since we have 3 i's, our component form, and I'll just write this component is going to be this one right here, 3, -4. And to make a quick sketch of this, for 3, -4, we go have an xy coordinate plane, and we go to the right 3 and down 4. So this is it in the lower right corner, and the vector looks like this, drawing an arrow to that coordinate pair at 3, -4. And we can create a reference angle by drawing a line segment straight up from that point to the x-axis. And so our opposite side is going to be -4, and our adjacent side up here along the x-axis is going to be equal to 3. So if we're looking for this angle here, we would find it by taking the inverse tangent. But before that, let's look at magnitude, to just be similar to the order we did the other one. So our magnitude, that's equal to, we have 3 squared plus -4 squared and that's going to be simplifying 2. 3 squared equals 9. Negative 4 squared equals 16. So equals square root of 25, and square root of 25 is 5. So our magnitude is equal to 5. Okay. Now for direction. Direction, we do the same way we did earlier. We know the tangent's going to be opposite over adjacent. So tangent theta, right over to the right just a little bit. Tangent theta is equal to negative 4 over 3. And taking the inverse tangent of this whole equation, what we have is our inverse and tangent, inverse tangent and tangent cancel each other, so we get theta is equal to inverse tangent of negative 4 over 3. Okay, so theta is equal to the inverse tangent of negative 4 over 3 so we get negative 3.13 degrees. And it kind of makes sense, right? Because we're rotating in a clockwise direction from the standard position to the right. So that makes sense. So another way we could handle this is if we add in quadrant 4 360 degrees, we could say theta is equal to negative 53.13 degrees plus 360 degrees. And to do that on a calculator, I think we can do it without a calculator, negative 53.13 plus 360 degrees. We get 306.87 degrees. Okay, so just different ways of writing the same thing, one with a negative rotation, one with a positive rotation. In quadrants 2 and 3, should you find a vector in quadrants 2 or 3, you'd have to add 180 degrees. Next and last odd number problem in this set is going to be number 37. And what we have are the standard unit vectors I and j. So reviewing what I wrote down earlier, we have I is equal to the standard unit vector 1, 0, and j is equal to standard unit vector 0, 1. And so we can take what this is going to be equal to, 7 times cosine 135 degrees times the standard unit vector of 1, which will be my 1. Okay? And then for j, we go ahead and take sine 135 degrees times 1. Well, if we distribute the 7 to both these terms, here, we are going to get 7 cosine 135 degrees, comma, 7 sine 135 degrees. And if we go back to what we had earlier, let's go back to problem 29. We have the magnitude times the cosine, the x-coordinate of the vector, if we'll call it, is the magnitude, and then multiply that by the cosine of that angle. And so we're given the direction in here. And I kind of like this direction form because it gives, one, an exact answer, and two, describes what we actually did to get to that point. So, coming back to problem 37, therefore our magnitude is equal to 7. And our direction is equal to 135 degrees, and that's a standard position type angle. So that would be our answers for, those would be our answers for problem number 37. Problem 38, very similar to problem 37. So good luck on all these other problems, these even order problems. And thanks for viewing.